The low-altitude economy operates in the airspace below 1,000 meters, introducing a new layer of commercial aviation directly above our streets. This specific altitude is uniquely vulnerable. High-density urban environments generate unpredictable microclimates and extreme wind shear that can materialize without warning mid-flight. During severe weather events, passengers naturally refuse to fly, and operators ground their fleets. The industry refers to these heavily restricted periods as ghost days. Society holds zero tolerance for commercial aviation crashes caused by unexpected atmospheric shifts. An aircraft cannot simply fall from the sky because the wind changed direction. Current regulatory sandbox testing largely ignores this threat. Many operators log nearly all of their test flight hours exclusively during optimal, sunny weather conditions, avoiding the very storms they must eventually navigate. Achieving a perfect pass rate strictly in ideal conditions creates a lethal blind spot. It completely invalidates a vehicle's apparent safety record the moment it is deployed into an open, unpredictable world. This diagram shows the baseline probability trap of an average city's climate, where roughly 80% of days feature clear weather and 20% experience volatile, severe conditions. If we apply a manufacturer's 99.99% sandbox testing pass rate solely to that good weather fraction, we secure an 80% baseline safety contribution. The untested 20% ghost day branch remains a variable. Assuming a baseline 50-50 coin flip probability of surviving an unexpected severe storm, the bad weather branch contributes exactly 10% to the overall safety margin. Combining these two metrics reveals the true system reality, a 90% overall safety rate. A 90% safety rate translates to 1 out of every 10 flights caught in unexpected weather facing catastrophic risk. Claiming an eVTOL is ready for urban deployment based on sunny day data is a statistical illusion. It treats densely populated cities as live testing grounds for unproven aircraft. Closing that 10% risk gap requires a shift in how aerospace engineering addresses environmental uncertainty. Traditional aviation safety protocols ensure that mechanical parts do not break. Autonomous electric aircraft require testing against environmental unknowns that confuse perfectly functioning sensor algorithms. The specific international standard designed to manage this complexity is ISO 21448, widely known as the Safety of the Intended Functionality, or SOTIF. SOTIF evaluates the absence of risk caused by functional insufficiencies. It measures what happens when the hardware works exactly as programmed, but the external environment behaves unpredictably. The tool to quantify this is the SOTIF index formula. The first variable measures mitigation completeness of known unsafe scenarios engineers programmed for. The second evaluates unknown unsafe scenarios, accounting for sudden environmental triggers designers failed to predict. Engineers face an operational paradox here. They cannot accurately calculate this unknown variable by sending human test pilots to fly blind into dangerous urban storms. SOTIF forces the industry to stop relying on weather forecasts to avoid risk, and instead systematically convert those unknown atmospheric threats into proven mathematical equations. If open-air test flights into severe weather are legally and ethically impossible, manufacturers must find a way to safely generate the critical data for that unknown SOTIF variable. The solution is hardware in the loop, or HIL, simulation. It provides a highly controlled, safe alternative to physical flight testing. HIL testing feeds highly complex simulated environmental physics directly into the physical sensors and the automated driving system of the actual aircraft. Hong Kong's proposed PAIS lab represents exactly this approach, a dedicated, high-fidelity HIL environment engineered specifically to test low-altitude economy vehicles. High-fidelity laboratory chambers can accurately recreate 90% of severe weather edge cases entirely indoors. HIL simulation replaces dangerous physical trial and error with rigorous, certifiable stress testing of autonomous systems. Returning to this probability diagram, we can input the specific data generated by HIL laboratory testing. We apply the 90% lab coverage and the newly proven 99.99% pass rate to the bad weather branch. The ghost days now contribute 18% to the total safety margin. We account for the final unknowns, the 10% of weather scenarios too complex for the lab to simulate, yielding a single percent. Summing the 80% baseline, the 18% verified lab data, and the 1% remaining unknowns, the realized system safety rate climbs to 98.99%. By moving the stress tests indoors, engineers mathematically lift the aircraft out of that 90% safety ceiling, where 1 in 10 bad weather flights remains at risk, and move toward a certifiable level of resilience. That 98.99% figure achieved in simulation serves only as a conceptual baseline. This logarithmic chart demonstrates the true standard required for commercial passenger transport. Categories like EASA's SC eVTOL demand a catastrophic failure rate of 10 to the negative 9th per flight hour, an uncompromising 99.99999999% safety threshold. Reaching this astronomical threshold requires organizing all accumulated HIL simulation data into a formalized safety case. A safety case is a structured, heavily documented argument asserting that a system operates with acceptable safety boundaries within a defined environment. Unlike traditional type approvals based strictly on part checklists, a safety case relies heavily on the internal credibility and data management of the organization producing it. That credibility is maintained through a Safety Management System, or SMS, an organization-wide framework ensuring risk mitigation is systematically enforced at every level of operation. Under the new UN Global Technical Regulation on Automated Driving Systems, regulators will not even review a safety case unless the company first proves they operate under a strictly audited SMS. Advanced mathematics and rigorous simulations carry no regulatory weight unless governed by an airtight, legally auditable organizational framework. The industry must redefine what constitutes a hazard. Conditions humans consider perfectly acceptable good weather, like a sudden burst of heavy glare or a patch of light fog, can blind computer vision algorithms entirely. Testing perception algorithms against these highly specific, momentary urban conditions in the open air is impractical and dangerous. The aerospace industry must execute a mandatory transition, abandoning the luck of sunny day sandboxes in favor of the controlled, high-fidelity rigor found in high-IL environments like PAI's lab. eVTOL manufacturers cannot wait for the storm to pass. They have to mathematically engineer their way through it. Converting unpredictable environmental risks into rigorous, evidence-based safety cases is the only viable path to deploying the low-altitude economy.